Welcome everyone to this webinar from Olympus NDT on understanding phased array time of flight calibrations for improved sizing using the OmniScan MX2. Our presenter today is Chris Magruder. Chris is the phased array AUT manager for Olympus NDT and has been developing and delivering phased array systems for over 12 years. He works with service companies and end users of all levels all over the world, providing phased array application development and support. To this webinar, he's bringing the best of his and our customers' experience with the latest phased array applications. This webinar is budgeted for about 60 minutes. The main presentation should last approximately that long. And so if there are questions, please type them into the Q&A panel on the lower right portion of your screen during the course of the presentation. Do not type them into the chat panel as we do not monitor chat from participants. If we don't get to your questions during this live event, they will be addressed personally either by email or by phone after the event is over. This presentation, along with the Q&A, will be archived on our website at www.olympus-ims.com. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, it's all yours.
Good afternoon, everybody. Thanks for joining us today, or good morning, depending on where you're logging in from. I see a real good mix of all different levels from our distributors and customers in attendance today. What we're here to talk about is improved wedge delay or time of flight calibrations for improved measurements. All of the MX2 and MXU OmniScan users generally learn how to perform the wedge delay calibration functions pretty early in the training. But we have an enormous amount of support that goes directly to this topic. And there's a few things only advanced users typically do that can improve that process. So today we're going to take you through some of those tools and explain what those calibration functions do and how we benefit from them. So I wanted to start off with talking a little bit about the focal law calculator, because it's the basis for everything we do on the instrument. Although we have calibration wizards to correct or fine-tune certain parameters, there's nothing more important that you can do than giving the calculator the correct information. So whether you're using the OmniScan MX2, which this calculator is a form of a wizard that makes the input simpler, or a computer-based calculator from Olympus or one other manufacturer, they're all divided into four basic groups of information. We see the 3 parts hardware and 1 part beamforming. So we have the probe, the part, which when we're talking about the part, we're only interested in the thickness and the velocity, and the wedge. When these 3 parts are populated, the user can ask for the beam information, and as long as they do that within the physics of the probe and wedge and material they're using, and within the limitations of the equipment, the software will return what you're asking for. Now, overwhelmingly, the culprit in poor calibrations or customer issues that we have to troubleshoot are regarding the wedge. Wedges come in all shapes and sizes and forms. We have standard ones, we cut them, but when we are looking at a beam that's not what we think it is, it's a different angle, a different focal point, it's exiting the wedge, different than what the software is telling us, it's almost always the wedge that is the problem. So a lot of the presentation today is issues with the wedges and how we overcome them. And again, even the wizards in the calculator of the MX2 are really just the same 4 basic pieces of information. The more complicated the wedge or the specialized application, these calculators come in all different shapes and sizes, and they're specialized for different applications. This is a generic one from TomoView, but they're all basically divided into the same 4 basic groups of information. Probe, material, wedge, all hardware, and then beam forming. This is the result of the calculator. So that calculator produces one or more focal laws. And all that is a set of timing delays placed on the element that will form our beam at the correct angle, focal depth, and exit point of the wedge. So one focal law equals one A-scan. And depending on the type of calculator you're using, like in the OmniScan, it would be a group of focal laws, either in a sector scan or linear scan configuration. Now, the wedge delay is built in to that calculation. So in this case, when I look at the result of the calculator for a 67-degree focal law, without any adjustment by the user or any calibration on a calibration block like you see here, the software predicts the wedge delay. And what that is, what the 54 microseconds that you see here, that is the time it takes the sound to travel from the probe to the exit point of the wedge, exactly like conventional UT. So we want to delay this part of our beam so that 0 millimeters on the A scan here equals the probe to component interface 0 here. And then we have an accurate scale reading for a fixed velocity of whatever we're inspecting, in this case carbon steel. So the software had all of the mathematics to accurately predict that. The velocity of this wedge, the velocity of the component material, and the wedge parameters, so that it can predict this number. Now, what we're talking about today, improved calibrations, is when that number is not perfect right from the calibrator or the calculator, what are the things we can do to make that accurate? In this case, we're looking at the 50 millimeter radius here, and we can see without any adjustment the software predicted that time of flight because it knows this velocity, and our wedge parameters were correct. So the software needs to know the 3 main parameters of the wedge. Depending on the calculator and what type of probe wedge configuration, there could literally be many, many parameters for offsets, but the primary information all calculators need to know about the wedge is this angle here. We need to know the velocity of the wedge, and we use a Rexolite because it has a fixed velocity that is very consistent in each axis, and it's also very consistent for different frequencies as well. And we need to know the height of the first element. This is the probe's relationship to the bottom of the wedge defined by element number 1. Now, in a conventional traditional wedge delay and in phased array, the wedge delay wizard is only designed to make minor corrections to this parameter because this wedge wears, or it's has a machining tolerance from the factory that you may need a level of precision greater than the machining. Minor angle errors result in degraded accuracy, but typically aren't the problem. The velocity of the wedge is always fixed, and it's a constant that we're going to use for our troubleshooting and some tips for improving our sizing later in the presentation. So again, when we're talking about calculators and wedges, angle, height of the first element, wedge velocity, and a wedge calibration for setting the wedge delay is based on height of the first element here. So normally, wedges are selected from the database. Olympus has a database of all of their commercially available wedges, and they also have a means of creating wedge entries for custom wedges we make or custom wedges customers make for themselves. These wedges come with a standard height and angle where it's all the same for the same model, but there's a slight machining tolerance. For the majority of our applications, selecting the wedge from the database results in a very accurate reading. But through the next series of slides, you're going to see we have a way of improving that for those applications that really need as the most accurate reading as possible. So when we program the MX2 or the OmniScan Wizard or one of the calculators, and we exit the calculator and we're looking at the result on the phased array sector scan display, one of the first things we want to look for is just the shape and size of our target on the side drilled hole notch or radius. Our ability to move this across the array by moving the probe, maintaining the correct depth across all of the angles, is the first indication that we've given the calculator the correct information. If the height of the first element, which is typical of wedge wear from manual use or from a scanner, is wrong, this indication remains flat, but will be slightly above or below the intended target, in this case 20 millimeters. If the angle is incorrect on the wedge or out of tolerance, or the velocity of the wedge or material is incorrect, you will see this moving up and down, and you will not have the ability to maintain the indication flat at a constant depth across all of the focal laws. So we're going to switch to OmniPC and take a look at a few files. So we've exited the OmniScan Wizard after creating our group, and we can see under our probe and part we have a standard probe and wedge from the database that we've selected. We haven't done any correction for time of flight, sensitivity, or velocity. We've simply input the parameters and generated our 45 to 70 degree typical sector scan. So we want to pay attention to the image that we see representing a side drilled hole. And this is a 1.5 millimeter side drilled hole on an IIW block. So as I move this, and whether you're moving it dynamically live or simply taking a clock scan by moving the probe on the calibration block and selecting pause on the instrument and creating a data file, we want to see that the indication, we'll put it at a constant position, and you don't want to trust your eyes necessarily because it's difficult to tell if this signal is maintaining its consistent position because it changes shape slightly with the beam spread. So as I move this across, I can see it's maintaining the correct depth at 15 millimeters. Now, to the codes and procedures or to any other specification, my ability to demonstrate this or check it quickly like I'm doing now verifies that the velocity of the wedge was correct, the velocity of the component calibration block was correct, the angle of the wedge, and the height of the first element. If one of those parameters was not what I thought it was or not what we gave the calculator, this would move either up or down, or it would be at a different position. Now, the tools that we're going to use under the wizard for calibration will make corrections to different parameters, but again, the only thing we can do without rebuilding the focal laws is correct the height of the first element. So we've verified right away that the signal looks good. Now, we get a lot of questions. Why does the shape of the signal change between a low angle, like a 45, and as we see it move over to 70 degrees? So it's traveling through the wedge farther, it's also farther out in time, so we get a beam spread effect, just like conventional UT. If I were to look at the echodynamic trace, and throughout this presentation, you're going to see me using this green envelope feature. There's a shortcut on the MX2 instrument on the left side panel that turns this on and off, and it's also available under the overlay display for the A scan here. Whenever we're measuring things and taking readings, we always want the very center of the energy or the peaked signal from a moving probe. And it makes very easy when you're using the envelope feature to verify that. So here we see at 70 degrees, we have a very long echodynamic with several data points that are very nearly the same amplitude. That's typical of conventional UT and in the phased array. So when we take the same indication at the lower angle, we will see a much different echodynamic. In this case, shorter, what we call the rise and fall time of the envelope signal you see here. We call this the echodynamic. The shorter the echodynamic is of the moving probe across the target, the more accurate your reading's going to be. So we're getting ready to move into the calibration, but even to the ASME Section 5 or similar type procedures, my ability to demonstrate what I just did has already verified my wedge delay. And for each focal law under the UT settings, beam, the beam delay or the time of flight for sound through the wedge is slightly different for each different focal law. And that's because the angles are traveling a longer path, and the exit point of the wedge is also slightly different. So those two things are going to be relative in the next couple of slides coming up. We've got a good beam. It looks like the calculator returned what we wanted, verifying that we've input the correct parameters, and now we can move to the calibration. So we're going to use a standard IIW block, not just for verifying the wedge delay, but we use this for verifying all types of beam parameters. There are several references on this block, including the circular target you see here for beam angle, the 50 and 100 millimeter radius for exit point and velocity calibration, and a series of side drilled holes as well. Whether you have a wedge that is suspect, whether you are troubleshooting problems from a customer or yourself where the beam does not appear to be what you've asked for from the software, or whether somebody gives you a wedge and you have no information. If you were given a wedge with no markings, it was made by somebody other than Olympus, and you need to develop or create the entry with the parameters, there's a way to do that ultrasonically and mechanically. And that's we're going to use this type of block to do all of those functions. And again, the overwhelming number of customer problems we see all normally go back to a wedge, the wrong wedge, a wedge other than what was entered into the calculator. So the first thing we want to do is verify that the exit point of the beam is exactly what the software calculated and matches what's really happening in the material. So we see a 50 millimeter radius and a 100 millimeter radius, and we're working in sound path here. So as I peak up the signal, and the benefit of doing this function on the radius and not a side drilled hole like you see here, is that this exit point is verified regardless of angle. There's no trigonometry. Whatever the beam is coming out of this wedge that I'm looking at in the software, I can find the exit point of that beam by using the reference marker here. Once I peak that signal up, and we see here's the 50 millimeter and the 100 millimeter, I'm going to put a little mark on the wedge, and I'm going to make sure that the exit point of the wedge is what was indicated in the software. So we see here that the exit point for that particular angle was 12.75 in the software, and it also matches the scribe line for the exit point on the calibration radius. So that's an immediate indication that most things are correct. That would be, indication number one if we used the wrong wedge, the wrong probe, the pitch was other than what was determined. So once we have the exit point, we will make a slight mark on it, and we will flip the calibration block over. We will take it from that same point where we referenced, and we will peek up this target. Okay, once we peek this target up using the envelope feature, the lines on the bottom of this block tell us what the angle is. And for those of you who are conventional UT people prior to using phased array, it's the exact same function. Sometimes our procedures require this. Sometimes we only do it for troubleshooting. But after verification of the beam exit and the beam angle, that would have isolated most problems we see. Or if we're working with a custom wedge that we're not sure if it's giving us what we asked for, that's the first two things that we do. So we see often from customers scan plans or groups that were created with angles beyond the steering range of the probe and wedge. In this example, we see a 45 to 70 degree sector scan. Most commercially available probes and wedges at shear wave are designed to work in that range. If I were to extend this to 40 to 75, from 35 to 80, I would start to reach the limits of the beam steering. And what I mean by the limits of the beam steering, what happens is you have the physical limits of UT, the physics, critical angles, mode conversion because of velocity, and you also have the limits of any given probe and wedge. The smaller these elements are, the more efficiently the beam can be steered. But when you program high angles that are outside of that range, what happens here is those beams mode convert to another velocity. And when they change velocity, they change angle. So once that happens, your measurements are no longer valid. They may have some benefit for detection, but if you're actually trying to measure something and the velocity, or calibrate it, and the velocity and angle has changed, it makes it impossible. So we need to work or understand the range of most of these probes. And again, a longitudinal wedge, either at an angle or 0 degrees, would have a very different range than a shear wave. And whether we check it on the IIW block or some of the commercially available tools and calibration blocks and standards like the ASTM E2491, we can define the limits of our beam and verify that what I'm asking for from the software is what is actually happening. In some of our automated procedures, when we're qualifying the procedure and inspection, the client or the client's representative may ask us to do a qualification for the ASTM E2491. And that's it covers many things, including linearity and beam spread, but the main one when we're talking about today regarding time of flight calibrations is angles. So I could record a small shot of my ability to detect this beam at the high angle and that beam at the low angle and define what that range is. The software in the OmniScan cannot tell you the limits of this because what may be acceptable for one customer may not be acceptable for another customer, and that comes in the form of a A-scan signal-to-noise ratio. Eventually, as I keep moving the angles up and looking at the individual A scan, I look at the depth and the shape and size of the hole and my ability to separate it from the noise on the baseline of the A scan. So we call that the signal-to-noise ratio. So once we've got our beam, once we have verified that it is at the correct exit point and angle of what the software has, now we could also make a minor adjustment to the beam delay, either to account for angular wear or wedge wear from use, or minor machining tolerances for the angle. Generally, the velocity is never an issue because we use a high-quality, most phased array probe manufacturers are using a Rexolite, which is a very consistent velocity. That's why they use it. So there's advantages and disadvantages to each of these, but in general, we are always going to use the sound path radius calibration when we need a precision measurement. And the benefit, and you'll hear this a couple times, is when I'm performing this function, it is not using the angle in my calculation. I've removed angle and trigonometry from my calculation. Where I'm using the side-drilled hole, that is very much a case. Now, we have many customers doing the sensitivity and time of flight calibration on this side-drilled hole, and as long as it's a small hole, and as long as you are using wedges from the database and you verified your beam, for the most case, that's going to be acceptable. But the radius will result in a much larger or much tighter accuracy. And what we don't want to see, so the wizard that we see here has options to work in either a sound path mode for the radius, and in this case, we'll see the radius reflection like this, and we will place a gate over it, or we can work in the true depth mode here on a side-drilled hole. Both of those exist. So we'll set our range correctly so that we can see the target, and we will position the probe so that the target's within our area of interest, and you'll see it's within the gate here. So what we don't want is to calibrate wedge delay on a large hole. The 3-millimeter holes, side-drilled holes, typical of an ASME calibration block of large thickness, you can see that if we were to tell the software that this is a 20-millimeter hole, the 70 degree is actually different than the 45 because they are intersecting the hole at different positions. The larger the hole, the greater the error. And performing a wedge delay in this type of inspection, you would actually be downgrading your inspection from the calculator results. So if we're using a radius reflector, a true depth reflector like this, we want the hole to be very small, 1.5 millimeters, like an IIW block, not a big reflector. In the radius, it's a precision reflector regardless of the angle. So entering into the wizard, we're going to tell the software the position of the radius. In this case, I could have either used 50 millimeters here or 100 millimeters here. I'm going to tell the software what the depth or the sound path is, and the software is going to make this adjustment so that 0 is here and my target is here. And we'll see that in the range. And the wizard will walk us through these every step of the way. We would typically do the entire range of the sector scan for the calibration. One reason that we might crop the last few focal laws off is if we were extending the beam beyond the steering range and we didn't want to ruin our calibration, but we wanted the benefit of seeing those last couple angles. The software, as I move the probe, is going to record the position and time of flight of every A scan, and if we see a if we see a signal outside the range of this window, it's telling us that we need to make a correction. Now, a lot of customer issues regarding why don't I see these two lines in the calibration window. These two tolerance lines here are entered. But if you don't see them, it's because typically this gate is outside the range of my A-scan. This scale here represents this gate. So if this gate was out here or before my range, I wouldn't see these indicator lines. So I want to make sure I set my gate over the target. We have it set here as a 90 millimeter start, a 20 millimeter width, and I will go to the next step. I'm going to move the probe slightly. Now, we have to move the probe because the exit point of every beam is slightly different. On a regular 0.6 millimeter pitch probe, it's going to have maybe a 5 millimeter difference between focal law 1 and focal law last. And I have a question here. It says, using an N55S wedge, is it possible to use an angle range of 40 to 89 degrees? If so, are ACG and TCG possible? Okay, now what happens is, and the answer to that is no. And it doesn't have anything to do with the software or a manufacturer or a different type of probe. But what happens is, depending on the probe model or pitch of the probe, at about 75 degrees, the beam starts to mode convert to another velocity. So just because we program an angle higher than that doesn't mean it's calibratable, because it's no longer linear, it changes velocity, and it changes angle. So we would define the limits first, and then your ability to calibrate it is what determines the range of any given probe. And again, the smaller the elements, the more beam steering. On our small Cobra probes that have a 0.25 millimeter pitch, we can steer the beam accurately and calibrate it up to about 75 degrees. Shear wave. The L wave versions of that can go much higher. So to answer your question directly, no. We could go on the probe he mentioned, N55S wedge with a 0.65 megahertz probe. We would define a range to that, maybe 72 to 75 millimeters, depending on the size of your calibration target. So we will create the scribe line here, and we will see that all of the focal laws are within the tolerance that we set. We will hit accept, and we will get a green W indicating that the wedge delay has been completed. Now, lack of a green W does not mean you're not calibrated. You could comply with all of the codes just by verifying what I've already discussed without actually using the wizard. But the wizard gives us an indication that the wizard was, the green W gives us an indication the wizard was completed, and we have a new calibrated beam delay for every focal law. Those of you who've done calibrations on side drilled holes, and in fact, I'm going to go ahead and jump back to the Omni PC. So in this case, prior to calibration, we have a very good sized, good shaped signal. If we look at another group, this is an example of what either a poor beam calculation or a poor wedge delay calculation looks like. It's immediately recognizable and should be an indication to the user that something is wrong. If you look at 45 or 50 degrees, it's very difficult to tell the bad wedge delay. But as I move the probe further out, so that I'm looking at it at 70 and 60, 65, and 70 degrees, notice the flat shape, elongated shape. We'll look at both of them side by side. So when we look at the two indications side by side, this is an immediate, as soon as we see this, we know there's either a wedge delay problem or a wedge problem with the calculator. And as we move these back and forth a little bit, we can see that shape changing. This is very common that we see this from customers. This results in degraded inspections, and in often cases, it's worse than just accepting the calculator value with no calibration. Okay, on a good calibration for the radius, okay, this is a clock scan. So all I did is I put the probe on the radius in the orientation that we saw. I moved the probe backwards, and I turned on the clock inspection. I slid the probe over the calibration block slowly, and then I hit pause. So now I can let go of the probe and relax, and I can take a good look at each angle. So if we see here, my 55 degree is at 50 millimeters and 100 millimeters. If I were to change another angle and do the same thing, peak this up, take the peak signals, again, 50 millimeters and 100 millimeters. If I can prove that all the way across the array, we're going to ensure that we're going to get very, very accurate, tight readings. This is what we're looking for. And in fact, if you gave the calculator the correct information, this is what should be generated directly from the calculator without any correction. And in this case, we have made a correction both for velocity and wedge delay. So this green indication here means that we've made a wizard change. Now, any of you who've done the wizard function on a side drilled hole, and remember I told you, if you're using a side drilled hole for your wedge delay or time of flight calculation, you are inserting angle, beam angle error, and the trigonometry needed to calculate the delay into your calculation. The radius doesn't do that. So if you've ever done this before and you get to the last couple focal laws, like 67 through 70, you hit calibrate, you check it, and nothing changed. You calibrate it again, and no matter how many times you hit calibrate, this does not get fixed. What that causes that, what it's a result of, is that on these high angles, you have an angle error. Means that your beam or your calibration target is far enough away so that the angle is not what the software thinks it is. So if we look at this 70 degree here, and again, for those of you, this is the 45 degree, this is the 55 degree, 60, 65, so on and so forth. So the last couple beams here, the software is using 70 degrees to run the trigonometry. But in fact, the real beam angle is maybe 68, 69, or 71. So it's running the trigonometry to make this correction based on 70 degrees when the real angle is other than 70 degrees, resulting in your inability to correct it. You'll also see, after completing the wizard function, that there is a wedge delay available from the UT general menu. This is used to manually tweak the wedge delay for all focal laws without having to use the wizard. There are some applications where that's beneficial, but for the majority of applications like typical code-based weld inspections, we never have to do that. It's normally a workaround when you don't have a calibration block and you have to make a minor tweak just to make your readings correct at one depth. But the difference between manually adjusting this is it will not wreck your focal laws and cause them to be rebuilt. If you make an adjustment here and you've already done your sensitivity calibration, it won't lose your sensitivity. So These next series of slides are some real typical questions we get all the time. What is the effect on the UT data if the wedge angle is different than the calculator? And by the way, so what we just did in that function, it corrected an error in this, as if the wedge were worn or had been modified. If this angle is correct or incorrect, it's going to affect everything, including the angle, focusing, and delay errors. Minor machining tolerances aren't going to affect us dramatically, but there is a tolerance on the machining of these wedges, and right now it's about 1/10 of a degree for what you buy from Olympus. What we see in other countries and from third-party wedge manufacturers, that wedge angle can be as much as 1 degree. So it can significantly affect us. There's nothing in the calibration tools that allow an angle error to be overcome. So we can change our delay to make one single target correct, but if you were to look at a target below it or above it, it would be off as well. So angle is very important. And if you don't know the angle, we're going to get to that shortly. There's a way of dealing with that. So can the angle of the wedge be measured if it is unknown? If somebody gave you a piece of plastic that you knew nothing about, can you measure this angle? It can be done both mechanically and ultrasonically. So if I laid a protractor down or traced this on a piece of paper and measured it with a protractor, I can get this angle. I can also measure this angle ultrasonically. We're going to have a procedure for that we use for troubleshooting. But inside the probe housing, these elements might be slightly misaligned. Again, with third-party probe manufacturers, we're seeing a high tolerance for this. So although you can measure the angle of the plastic, you couldn't easily measure the angle of the probes elements inside the housing mechanically. You can measure them ultrasonically, and that's where we're going shortly. What is the effect on the UT data if the height of the first element is different than the calculator? In this case, the beam angle remains correct. The beam focusing is slightly short or long depending on this error, and the wedge delay is incorrect. So in this instance, the software can correct everything. It can make this correct, recorrect the beam delay, your angle's okay, just like a worn wedge for manual UT or a slightly modified wedge from a contour. We can correct this in the software, and that's what we normally do. Where we see customers that really have problems with their beams is when they're using this function to correct angle or to correct material velocity instead of what it's intended to for wedge delay. Does normal usage result in wedge wear that will change the height of the first element? Yes, of course. So as this wedge wears, this distance changes. And it typically doesn't wear very consistently. In other words, as this wedge wears, there's a very good chance that the height of this element and the height of this element will not wear at the exact same rate, which results in a changed angle. That can be minimized with carbide wear pins or care on the wedge. Can the height of the first element on the wedge be measured if it is unknown? In other words, again, back to our example, if somebody hands you a piece of plastic you know nothing about, can I measure this? It can only be done ultrasonically. It cannot be done mechanically. In other words, you cannot see the position of the element inside the housing, and there's a gap and an impedance matching layer in between the probe and the wedge. So I must measure this ultrasonically, not mechanically. And again, that's what we're going to see shortly in a procedure that we use for troubleshooting. So when we are troubleshooting probes and customer problems of any kind, beam problems, something doesn't look like what I think it's supposed to look like. We told you before we're going to verify the first thing, the shape and image of the side drilled hole in the sector scan. We're going to verify the beam exit point on the software and the radius. And then we're going to verify the beam angle. So in addition to those three troubleshooting methods, another thing we do is what's called inspecting the wedge. We're going to do an acoustic wedge verification that basically means we're going to inspect our wedge and get the parameters to a tighter tolerance than the factory is capable of manufacturing them. So what this does is we're going to do a contact inspection with no wedge, and for the component inspection velocity, we're going to enter the velocity of Rexolite here. That will enable us to measure the height of every element in relationship to the bottom of the wedge. Even though the elements are oriented in this axis, the angle of the wedge, the beam spread is going to give us the 0 degree measurement. So in this case, element 25 is exactly 19.63 millimeters. We're going to measure the height of the first element here and the height of the last element here. And again, we'll switch to the Omni PC to take a look at that. And all of the data files that I'm referencing for this and this presentation is going to be available from a link you're going to see on the last slide of the presentation. So you'll be able to take a look at this yourself in OmniPC. So I said element 25. What I'm doing is I'm doing an inspection using only a contact probe, no component. Contact wedge means no wedge. This is Rexolite. This is the wedge I'm inspecting. So under UT, I enter the velocity of the wedge, and it's very consistent that makes this possible. It's very accurate. I'm going to build a focal law of a linear scan with a one-element step all the way across the probe. That means that this is the A scan from element 1. This is the A scan from element last, and I can see them independently from each other. So I'm going to use this reading here. So this is the wedge to probe interface, and this is the bottom of the wedge. And I can get a very, very accurate reading of 11.15. At 0 degrees, the depth and the sound path are going to be the same. I'm going to write that number down, 11.15 height of the first element. And that's one of our critical parameters needed for the calculator. And then I'm going to measure the last element here. Element 64 is 33.46. I'm going to write that down and remember it. If I'm inspecting the wedge, I can arrive at all of my wedge parameters from this setup. Going back to our presentation. So this was the first element position here. This was the last element position here. And I'm going to use those two readings to plug them into a formula you see here. If I know the height of the first element, the height of the last element, and I know the pitch of the probe and the total elements in the probe, I can determine the real angle of the wedge. So what I need is this angle, and I now have it, height of the first element. I measured this, and the I can arrive at all of the things I need for a more accurate time of flight inspection. So on the wedge I'm looking at, the database has a standard angle of 36 degrees and a height of 11.02. By doing this function, I'm arriving at an angle more accurate So I will plug these values in as either a custom wedge or create a new wedge, and I will end up with a much more accurate calculation from the beginning, so I don't have to make any modifications during the wizard calibration process. Now, other little tips that are going to help us as well as these carbide tips that are used in the automated inspections with the mechanical scanners. These tips affect our wedge delay a lot. They're not designed to create a gap between the probe and the wedge, the wedge and the component. They're designed to not wear the Rexolite when they rub. So these need to be short and even with the component surface. They need to be secured in place with Loctite or a set screw with other types of designs. Sometimes we'll put a sandpaper on the pipe here, and we will rub the wedge back and forth so these wear pins end up being worn to the same radius and the same contour as the pipe. All those little things are going to help us in our accuracy. It's very important that you know what gate mode you're working in. Those of you who don't have these options in your OmniScan, you should go to the website and upgrade them. It's a release that's not so recent, but customers who've never had a reason to upgrade their software will benefit from this new feature and other features. But this gives us a wider range of gate options. And whether I'm using peaks, like you see here, or leading edges, it's very relevant to the accuracy of our readings. Selecting edges, it will display the mode in the DA and PA readings and SA readings. And working in peak modes like I've been throughout this presentation, and we typically do for weld inspection, you'll see it here. Anytime you're in peak mode, you want to make sure that you've set the amplitude so it's not saturated, it's not over 100%, or you will could get an inaccurate reading. So be aware of your gate mode and make sure if you're in peaks that you are not saturated. In leading edges, it doesn't matter. You can be saturated because it's taking the reading from the gate interface. Increasing our point count value will also improve our results. By increasing the point count, which is under UT Advanced, the OmniScan default is 320 points, and we use a type of compression that allows us to never lose amplitude, but lose resolution, resulting in smaller data file and faster acquisition speed. So again, increasing the resolution on the UT axis is directly related to accuracy of readings, but is also related to file size and scanner speed. Recent probes, a trend we see in the pipeline and the Cobra type inspection, we see more and more probes with an internal radius, so that they are mechanically focusing with the focusing of the phased array. On probes like this, typical of our Cobra probes for small diameters or our Pipe Wizard probes for pipeline inspection, there is a Rexolite insert inside that probe. Then there's also a Rexolite wedge. So that wedge insert for the curved array must be accounted for in the wedge parameter for the wedge delay to be created accuracy. The procedure I demonstrated here is going to allow you to put that Rexolite wedge inside your wedge as well, so you get the real value. Sorry, I had to back up to demonstrate that. We would recommend upgrading your wedge database as well if you've never had a reason to do it. There have been some changes. We reevaluated all of the wedges to make them a little bit more accurate, including the Cobra wedges for the internal insert to account for the radius. Those have all been corrected in the database now. So if you're a Cobra user and you've been out, you haven't upgraded your software in the last year or so, we recommend going to the website and upgrading your wedge database, both for TomoView and the OmniScan. So this presentation and the data files that I referenced can be downloaded from this address for the next week. We'd recommend taking a look at those files in OmniPC and going through some of the same functions I've gone through. There were some questions that were in the panel that we're not going to have time to get to, but I will answer all of those for everybody through the email. So again, the point I wanted to emphasize, most of our problems are resulting from the wedge, not from the probe or material velocity. Radius wedges or radius calibrations in SoundPath are more accurate when you need calculator inputs more accurate than the defaults that come from the factory. You have a way of measuring those ultrasonically. So for the majority of all of our applications, accepting the factory defaults and using the normal calculator wizard and calibration functions are going to result in normal, accurate readings, but the tools we've talked about today are going to allow those to be more accurate and improved upon, and more importantly, they're used for troubleshooting as well, the beam angle. So we're going to leave it right there. I will answer questions we didn't have time to get to via email. I want to thank everybody for attending. I saw a lot of familiar names and companies in the list, and look forward to you guys participating with us for the next webinar. So I will turn it back over to our moderator and sign off. Again, thank you very much for attending.
Thanks, Chris. On behalf of Olympus, I'd like to thank Chris for his participation today. Thanks very much to all the rest of the attendees for joining us. We hope this material that was presented was informative and useful. The webinar, along with the combined Q&A from both sessions today, will be archived on our website at www.olympus-ims.com. That's going to do it for today. And again, thanks to everyone for participating, and we'll see you on the next webinar.